Welcome to lesson 17 on power system analysis. In this lesson, we will continue with the power flow problem that we discussed in lesson 16. Well, here we will recapitulate some of the important points of the power flow problem. Then we will talk about some of the computational aspects involved while solving this power flow problem. We will take up one method for solving power flow problem, namely the Gaussian method, and we will take one small system example to illustrate how we carry out this power flow problem using Gaussian method. Well, on completion of this lesson, you should be able to explain the significance of power flow problem for large systems, develop the Gauss-Seidel iterative technique for power flow solution, and should be able to solve power flow problem using Gauss-Seidel method. Well, if you remember, in the last class we talked about the power flow problem, where we showed that the power flow equations are coming from the network equation of the system, that is I bus is equal to Y bus into V bus, where I bus is a n:1 vector of the current injections into the bus bars of the power network. Y bus is a n:n matrix of the admittances, and V bus is the voltage phasor at the n buses of the power system. We also saw that we can write this equation for at any individual bus k as current injection I k is equal to summation from n is equal to 1 to capital N, where capital N is the number of bus bars, is y k n into V n, where y k n is the admittance or the elements of the k and knth element of the Y bus, and V n is the voltage phasor at bus n. From this equation we can write the complex power injection into a bus k is equal to P k plus j q k, and where P k is the real power injection and q k is the reactive power injection. This is equal to V k into I k conjugate. Now, we know this I k from this equation here. So, substituting we can write P k plus j q k is equal to V k into conjugate of this I k. So, summation n is equal to 1 to capital N y k n V n, where k varies from 1 to n capital N, where capital N is the number of bus bars in the system. V, as I said, at bus n is a phasor which will have a magnitude V n and an angle delta n. I am sorry, this should not be k n, it is delta n, and y k n is the k nth element of the Y bus matrix, which again is a vector, where y k n is its magnitude and theta k n is its angle. Now, substituting this in the equation, we get P k plus j q k is equal to V k summation n is equal to 1 to capital N y k n V n e to the power j delta k minus delta n minus theta k n. That is, we are writing all the angles here, where delta k is the angle associated with V k, delta n is the angle associated with V n, and y k n theta k n is the angle associated with y k n. Now, since we have used the conjugate, so the angle associated with V n and y k n are both negatives. So, this is the equation that we get, from which we can separate out the real and imaginary parts. Then we can write the real power injections into bus k is equal to V k summation n is equal to 1 to capital N y k n V n cos delta k minus delta n minus theta n, and similarly the reactive power injection into bus k is equal to V k summation n is equal to 1 to capital N y k n V n sin delta k minus delta n minus theta k n. So, these the equation for injection power injection we see here is related to the voltage magnitude and the angle at various bus bars. So, this is basically this equation or this set of these two equations are forming the relationship of power injection and voltage magnitude and angle at various bus bars, and these are the power flow equations for the power network. Now, what are the characteristics of this power flow equation? We had seen that these equations are algebraic equations because they are basically dealing with a static system. Also, we find that these equations, since they involve cos and sin terms here, as well as they have the multiplication of voltages involved, therefore, these equations are nonlinear equations, and therefore, in general we need iterative methods for solving this. The power flow equations relate the injections, the real and reactive power injection at a bus in terms of voltage, magnitude and angle at various bus bars in the system, and the admittance matrix of the system. That is, P q is related as or can be written as a function of V delta. So, this is how we write our power flow equations. Now, we know that in a power system we have various loads, generation and the voltages involved. Now, loads are something which we have no control on, that is, a power system operator has no control on the loads, it is dependent on the consumers. So, we call these loads the PL and QL at all the buses as uncontrolled or disturbance variables, that is, they are under no control of the operator, and so they can be treated as some disturbance in terms of any change which is occurring in these loads. Now, generation can be changed by the operator, and therefore, these are control variables because operator can always control these in such a way that the real power and reactive power is always balanced with the load. And the voltage at various bus bars, in fact, the voltage at all the bus bars form the state variable for the system, because if we know the voltage magnitude and angle at all the bus bars, we can always find out the power flow in each and every line or the power injections at different bus bars. So, these are called the state variables. For a given operating condition, loads and generations at all buses are generally known. That is, when we are trying to do this power flow study, what we do is, or what we need is basically a given operating condition, which is basically trying to or asking for what are the loads in the system at that particular instant or that condition which we want to analyze. So, all the loads and the generation for that particular operating condition will generally be specified. So, given these loads and generation, the problem of power flow is to find out the voltage magnitude and angle at all the bus bars. Now, as we had said earlier, there is one problem in doing this, because we cannot know beforehand all the generations. All the loads are known to us, but generations are under our control. So, one can say that we should know all the generation, but there is one problem. The problem is, till all the generations are available, we do not know what is the loss in the system, and since we do not know the loss in the system, we cannot know all the generation, because the sum of loads and the losses must be equal to the total generation. And to overcome this problem, what we do is we choose one bus as a reference bus which takes up all these losses. So, since the losses are not known beforehand, we consider one bus which will take up all these losses, which we will find out after the solution. So, at one bus we cannot specify the generation. Generally, this is a bus which has very large generation available, so that there will be no problem for it to take up the losses. This bus in power system terminology is called a slack bus, because it takes all the slack, that is all the losses in the system. So, we have different types of bus bars in a power system, and in fact, the solution of power flow equation depends on the type of the bus bars that we have. As I just now mentioned, we have a slack bus where we do not specify the generation, but we specify the voltage magnitude and the angle. Since this bus is a reference bus, the angle that we specify for this is normally 0 degrees, and since it is a generating bus which has its own voltage regulator, therefore, the voltage magnitude is fixed and we specify the voltage magnitude at this bus. So, swing bus has voltage magnitude and voltage angle specified, whereas other generator buses we can control the real power. So, we have the real power which we specify, and since most of the generator buses also have a voltage regulator, so the voltage at the terminal can be fixed, because the regulator automatically will adjust it to that voltage. So, we have a voltage specified at these buses, and these buses are called PV buses. Some of the load buses also, where we have reactive power sources available, can maintain its voltage at a specified value. So, those buses also can be treated as PV buses, that is buses where real power and the voltage magnitude is specified are the PV buses. The third type of buses are those where both real and reactive power are known. These buses are called PQ buses. Most of the load buses where we do not have any generation, we know the loads, that is the real and reactive power load at all these buses. So, therefore, we see that we have 4 variables associated with every bus: the real power injection, the reactive power injection, because if we know the generation and the load at a bus, we can subtract the load from the generation to get the injection. So, we have real power and reactive power injections known at the buses. The other variables are voltage magnitude and angle delta. So, P I, Q I, V I and delta I are the 4 variables associated with each bus I in the power network. Now, depending on the type of bus, 2 variables are specified and 2 variables are not known, and they need to be computed by the load flow or the power flow solution. Now, as I said, swing bus we have V and angle delta both specified. So, the variables which are to be computed are P I and Q I, that is real and reactive power injection. For PV buses we have P and V specified. So, the unknowns or the variables which need to be computed are angle delta, voltage angle delta, and the reactive power Q injection. At the PQ buses, both P and Q are known, and the unknowns which need to be computed are voltage magnitude and angle, that is V and delta. Now, let us take a sample 5 bus power system which we had seen earlier. Now, in this system we have at bus 1 PG and QG generation, we have at bus 2 PG2 QG2 generation, PL2 QL2 loads. At bus 3 we have PG3 QG3 generation, PL3 QL3 loads. At bus 4 PL4 QL4 loads only, there is no generation, PL5 QL5 at bus 5 are the loads, and these buses are connected by various lines L1 to L6 as we see here. Now, if we know PG and PL and QG and QL, we can find out the injections at those buses, that is PG minus PL will give me the real power injection, QG minus QL will give me the reactive power injections. At those buses, load buses where we do not have any generation, PG is 0. So, the injections will be minus PL minus QL for those buses, like for bus 4 the injection will be minus PL4 minus QL4 and so on. Now, for this system, suppose we are given the data. Now, the data which will be provided, normally we have two kinds of data for this system which we require for the power flow solution. The data is in form of bus data and line data. Now, let us see what is generally given in bus data. Bus data, what we have is of course the serial numbers, and then we have the bus types. Bus types are swing bus or PV bus or PQ bus. So, if we look at this system, we have specified our bus 1, this bus, as our swing bus, whereas the bus 2 is specified as a PQ bus. So, swing bus, what we have known variable or the specified variable, the voltage magnitude 1.03 per unit is given or specified, and the voltage angle 0 degree is specified. At this bus we may have PLQL, but generally we can always find out injection, and then knowing the generation we can find out the loads. So, anyway, here it is 0 0. Bus 2 is a PQ bus. So, here what we have specified, V and delta is not known. What is specified is PG, QG, PG is 1.4, QG is 0.8, PL is 3.0 and QL is 1.2 per unit. So, here PG, QG, PL, QL are specified. So, PG minus PL and QG minus QL will give me PI and QI at this bus, the real power injection and reactive power injection. Bus 3, again this is a generator bus where we have P and V specified, that is the real power generation is specified as 2.2, the voltage which is specified is 1.05. The load at this bus is 0.8 per unit PL and QL is 0.4 per unit. Now, since we know this PG and we know this PL, we can find out PI. So, PI is specified and V is specified. So, and one more thing which is specified at this bus is that most of the generators will have limits on reactive power generation. So, QG max and QG min is also specified here. So, QG max is 3.0 per unit, QG min is minus 1.8 per unit, that is the generator can act both in providing the reactive power as well as absorbing reactive power. Generators have some limits based on the field current for the reactive power generation, and also because of stability limits. So, QG max and QG min are the limits. Now, when we do a load flow and we find out that the value that we compute for this particular bus, say QG, comes out to be more than 3.0, then certainly we cannot accept that solution, because this generator cannot supply more than 3 per unit reactive power. So, in that case what we need to do is we will fix QG at this bus as 3.0, and then the voltage of 1.05 or whatever is the specified voltage will not be possible to maintain, and therefore, voltage will be made a variable, and this bus will be changed into a PQ bus. So, and then a load flow will have to be done again with this new value of Q fixed at this bus. The other two buses, bus 4 and 5, are PQ buses. They are load buses where both real and reactive loads are specified. So, this is a kind of data which will be given for performing a load flow. Of course, the other data which we need is the line data, where we need the resistance, reactance and the susceptance of the line to be known, so that we can find out or formulate the Y bus matrix or the network matrix for the system. So, for this system we have, for line between bus 2 and 4, resistance is given as 0.0090, reactance is given as 0.10, the susceptance is given as 1.72, that is the line charging susceptance, and we also have a maximum rating of the line, that is, you can't allow more than a certain amount of power to flow on the line, that is limited by the current carrying capacity of the conductor of that line. So, the data like this R, X, G, B and maximum MVA limit for the line will be specified. This data is used for forming the Y bus matrix. Now, if we look at this system, what we find? We find that we have 3 type of buses. Now, we have one is a swing bus. How many swing bus we have? We generally have only one swing bus in a system. So, we have one swing bus. What are the specified quantities at this bus? Both voltage magnitude and delta angle associated is specified at this. And so, how many equations we need to write for this bus? Since both voltage magnitude and angle delta are known at this bus, and the load flow needs to find out the voltage magnitude and delta at all the buses. Since this is already known, so we do not need to write any equation for this bus. So, number of equations needed for this bus is 0, number of state variables required to be computed is 0. The other type of buses are this PQ bus. Now, how many PQ bus we have in this system? If we go back, we see that we have bus number 2, bus number 4 and bus number 5 as PQ buses. So, we have 3 PQ buses in the system. At PQ buses, what we have specified quantities are both P and Q, that is real power injection and reactive power injection are specified. So, how many equations we need to write at these buses? We need to write 3 into 2, that is 2 equations for each bus, that is the Pi and Qi equations in terms of V and delta and Y for each bus. So, we have 3 buses like this. So, we have total of 6 equations, and how many number of state variables we need to find for these buses? We have V and delta to be found for each of these 3 buses. So, we have 6 state variables which we need to find. Now, the other type of bus in this system is a PV bus. We have one PV bus in this system. Sorry, we have bus number 3 as a PV bus in this system. So, at this bus what is the specified quantities? The real power injection is specified and the voltage magnitude is specified. So, what we need to find out at this bus? We need to find out angle delta for this bus. So, number of state variable is 1, and how many equations we can write for this bus? Since we know only Pi, so we can write only one equation for this bus. So, in total if we see, we have 5 buses, out of which there are 10 quantities which are specified, and we have total number of equations for the system that we can write are 7 number of equations, and total number of state variables that we need to find are 7. So, we have 7 equations and 7 unknowns which we need to find out. So, this is very easy to do this, except that the equations that we have are nonlinear algebraic equations which require iterative solution. So, okay, now let us go into how we find out these the solution for the power flow problem. Here we will take up one method of solution, iterative solution, that is the Gauss-Seidel method. Now, this method, for this method we start with again the basics. I bus is equal to y bus into v bus, that we know, and we know for any bus k the current injection I k is summation y k n v n, where n varies from 1 to n. Now, if we write the complex power, we write S k is equal complex power injection S k is equal to P k plus j q k. This is equal to V k I k conjugate. This we had already seen, and this if we want we can write this I k, replace this I k here, then we have P k plus j q k is equal to V k summation y k n v n, n is equal to 1 to n, capital N, the conjugate of this for all the bus bars. This can be written, that is k is equal to 1 to capital N. We know that from this relationship, if we see P k plus j q k is equal to this, we know, therefore, we can write I k is equal to P k minus j q k into V k conjugate. That is, instead of writing P k plus j q k, if we take the conjugate of that, then P k minus j q k will be equal to V k conjugate I k. Therefore, we can write I k is equal to P k minus j q k divided by V k conjugate. Also, we know I k is equal to summation y k n V k n, which we can write as I k is equal to y k 1 v 1 plus y k 2 v 2 plus so on y k k v k plus so on up to y k n v n. Now, from this equation, if we leave this term and take all the other terms on the other side and replace I k by this relationship, then we have V k is equal to 1 by y k k. If we take this side, then we and divide this by y k k, then 1 by y k k is equal to P k minus j q k by V k. This is for I k we are writing, minus all these terms except this term. So, n is equal to 1 to k minus 1 y k n v n plus n is equal to k plus 1 to n y k n v n. So, this is the equation that we get. That is what we have done, is we have tried to write the equation for finding out V k, where k is equal to 1 to n. That is for each bus we can write this equation. Now, for the time being, we will consider that we have only PQ buses and swing bus in the system. there is no PV bus in the system. We will take care of the PV bus later. So, we can write this equation for all the buses except the swing bus. So, what is the iterative procedure for solving this? First, we will make an initial guess V I 0 and delta I 0. Normally, what we do is we use a flat start, that is V I 0 is equal to 1 per unit and delta I 0 is equal to 0 degrees. This is an initial guess that we make, because we know that the voltage magnitudes are at all the buses under normal operating condition are going to be very near to 1 per unit only. So, an initial guess of 1 per unit is good enough. The value of delta angles are also not very far away from 0. They may be 10 degrees, 15 degrees, 20 degrees or so. So, since we do not know those, the initial guess we make is all buses have delta as 0 degree. So, with this, use this solution in power flow equation to obtain a better first solution. That is, what we can do is, if we substitute that value of V magnitude and delta angle at for all these buses, and we know this Pk, Qk and this Vk also will be the guess value, then we will get one value of Vk, which we call as the first improved estimate of Vk. So, from the guess we can get an estimate of the value of voltage. So, a better solution or first estimate we get. So, use this solution in power flow equation to obtain a better first solution. After we have got this value, now we can replace the old values by this value and again get a better estimate or a better solution. In this way, we will keep on iterating till we find that the solution has converged. That means, the change in the value from the previous iteration to the next iteration is not very large, that is, there is hardly any change which is taking place. Okay, so, if we want to do that, we can write this in a mathematical form or in equation term like this: Vk at iteration I plus 1 is equal to 1 by Yk k into Pk minus jQk divided by Vk, I am sorry, Vk conjugate, here we should have iteration I, minus summation Ykn Vn at iteration I plus 1 plus summation Ykn into Vn at iteration I. Now, here you see what we have done is, as we keep on updating, the previous values are being replaced by the updated values. So, if we are doing, say, finding out the value at I plus 1th iteration for bus 5, then we already know the I plus 1th iteration value for bus 1, 2, 3 and 4. So, that those 4 bus values, the updated value, that I plus 1th iteration values can be substituted here, right. So, this helps in getting a better solution faster or reducing the number of iterations required. So, what we do is we keep working on this, replacing the older values by the new values and compute it for all the buses where for that is for k is equal to 1 to n, and we do this till for all the buses, all buses k, I plus at Vk I plus 1 minus Vk I, the mod value, that is the magnitude of this, is less than some tolerance value that we have specified. So, if we do this iteratively like this, then we will reach a solution. When this, that is the update and the previous value, there is hardly any change at all the bus bars. So, we can see the algorithm steps as with PGI, QGI, PDI and QDI known, calculate bus injections Pi and Qi. Form the Y bus matrix. Next, set the initial voltage Vi0 delta I0. You can use a flat voltage start, that is Vi0 is equal to 1.0 per unit and delta I0 is equal to 0 degrees. Now, iteratively solve the equation as shown earlier. Vk I plus 1 is equal to 1 by Ykk into Pk minus Jqk Vk conjugate I, that is value at iteration I, minus summation Ykn Vn at iteration I plus 1, that is the updated value, plus summation Ykn Vn I, that is the value which is available at ith iteration. Since the new value at I plus 1th iteration for these voltages are not known, so these are the latest value which is available. So, this is done to obtain new values for the bus voltages. Now, till now we have assumed that there are no PV buses on the system, but as we know the voltage magnitude at the generator buses or buses where reactive power sources are available can be maintained at a pre-specified value. So, we have voltage magnitude specified at these PV buses. So, in that case, as we said earlier, that if we find we can work out with voltage magnitude fixed at these values, and only thing that we need to do is compute the value of delta for this. So, if we write Q at this PV bus, Qi is equal to minus of imaginary part Vi conjugate into Yik Vk, k is equal to 1 to n, that is, this is for the current, and so V conjugate I, it gives me the conjugate of complex power, that is P minus Jq. So, Q is minus of imaginary part of this term. So, we have got this equation. Now, we can always write the equation in terms of Q here as Qi at r plus 1th iteration is equal to minus imaginary part of Vi r conjugate into summation Yik Vk at r plus 1th iteration plus Vi at rth iteration conjugate into summation Yik into Vk at rth iteration. Now, the revised value of delta can be obtained from this, as we know that delta is nothing but angle of V. So, delta at r plus 1th iteration, delta I at r plus 1th iteration is angle of Vi at r plus 1th iteration. Therefore, we can find out the angle of that part very easily as angle of A I r plus 1th iteration value into Vi r minus summation Bik Vk r plus 1th iteration minus summation Bik Vk r, where Ai is given by Pi minus Jqi at r plus 1th iteration divided by Yii. So, from using this we can find out the angle, and this angle will be used as an update for the next iteration. The solution procedure for PQ buses remain the same. So, now we will take a small example to illustrate how we can solve a power flow equation using this Gauss-Seidel technique. Now, here we have a system shown in figure here, a simple 2 bus system where we have a bus 1 where we have real injection, complex power injection, the voltage magnitude at this is given as 1 plus J 0, that is magnitude is 1, angle is 0 degrees for this. This is connected to another bus through a transmission line whose impedance is J 0.5. Of course, this line will have susceptance and other things. For the simplicity of solution, we have neglected those things. Now, at bus 2 we have a capacitor connected, which is injecting Qg2 power, which is equal to 1 per unit, and we have a complex load SD2 is equal to 0.5 plus J 1.0. So, this load or the injection at this bus is known, the voltage at this bus is known, and we need to find out the voltage magnitude and angle at this bus. This bus will be acting as a slack bus, because here both voltage magnitude and angle is specified, and also we do not know what will be the generation at this bus till we know the loss here. So, if we take that into account, then first we calculate the elements of the Y bus matrix. For Z is equal to J 0.5, we have Y11 will be equal to 1 by J 0.5, which is minus J2, Y12 will be negative of this ZL 1 by ZL. So, that is equal to Y12 is equal to J2, Y21 will be similarly equal to Y12, that is equal to J2, and Y22 will again be equal to 1 by ZL, that will be equal to minus J2. Now, if we go back to the equation that we had set up for the this is the equation that we have set up for the Gauss-Seidel method, then if we substitute the values here in this case, then we have V2, this is the unknown thing, voltage V1 is known, n plus at n plus 1th iteration is 1 by Y22 S2 conjugate, that is P minus JQ. So, S2 conjugate divided by V2 n conjugate minus Y21 into V1. So, this is the equation that we have for updates for V2. So, if we start with the V1 we know is 1 angle 0, S2 is SG2 minus SD2. So, if we look at this, SG2 is QG2, that is J 1.0, SD2 is 0.05 plus J 1.0. So, we have SG2 which is 0 plus J 1.0 minus SD2 which is 0.5 plus J 1.0. If we do this, then we get S2I equal to minus 0.5. Sorry. So, S2 or the injection at bus 2 is equal to minus 0.5. So, putting the values of V1, S2, Y22 and Y1, Y21 in equation 1, we get V2 n plus 1 is equal to minus J 0.25 divided by V2 n conjugate plus 1, because we have taken J by this is, if we substitute the values here, I am sorry, here Y22 is minus J2, right. So, this if we substitute here, then we will get this V2 as, I am sorry, V2 as this, and we start with a guess taking V 2 0 as 1 angle 0 and iterate using equation 2, then we will get, we have V 2 0 as this. So, putting the value here, we will get V 2 1 as minus j 0.25 divided by 1 plus j 0 conjugate plus 1.0. So, this will give me as 1.030776 angle minus 14.036 degrees. Now, if we substitute this value now for V 2 in that equation, then we will get another updated estimate, that will be V 2 at second iteration, which after substituting the values here, we will get this value as 0.970143 with an angle of minus 14.036. So, if we now substitute this value of V 2 for the third iteration, then we will further get a modified estimate and so on. If we keep doing that, then we will get the values after a third iteration as 0.970261 angle minus 14.93. If we substitute this value of V 2, and then we will get an estimate which will be fourth iteration estimate as 0.9662 with an angle minus 14.9314. If at the fifth iteration, after substituting the value obtained at fourth iteration, we will get this as 0.96623 angle minus 14.9950, and sixth iteration we will get this value after substituting the value at fifth iteration as 0.96594 angle minus 14.9950. So, what we are finding is that the value after fifth iteration, when we get the value at sixth iteration, the difference is very small, and so we can say that the process has converged in 6 iterations, and the final value of the voltage V 2 that we obtain from this is 0.965948 with an angle of 14.9950. So, this is the solution for the load flow. Once we get this voltage V 2 at this bus, then what we have is we can calculate the line flows, because we know the voltage, we know the admittance of the line. So, we can find out the current and power flowing on the line. So, therefore, what we find is, starting with a guess value of 1 angle 0 degree for V 2, we achieved a solution or a converged solution in 6 iterations for this simple system using Gauss-Seidel iterative method. So, this is all for today's lecture. For today's lesson, we will talk about Newton-Raphson method of power flow solution in the next lesson. We will also talk about some of the convergence characteristics of the Gauss-Seidel method in that lesson. Thank you. Welcome to lesson 18 on power system analysis. In this lesson, we will continue with our discussion on power flow solution methods. In the last lesson, we discussed about the Gauss-Seidel method for power flow solution. In this, we will continue with some of those aspects, and then we will talk about newer method for power flow solution. Well, in this lesson we will start with some computational aspects of Gauss-Seidel method. Then we will talk about power flow solution by Newton-Raphson method. We will then talk about direct solution of linear algebraic equation, as we will find that Newton-Raphson method finally boils down to solving a set of linear algebraic equations, and then we will take a small example of solving this linear algebraic equation by the Gauss elimination method. Well, the objective of this lesson is that at the end of this lesson you should be able to explain the characteristics of the Gauss-Seidel method, develop Newton-Raphson iterative technique for power flow solution. You should be able to solve a set of linear algebraic equation and solve power flow problem using Newton-Raphson method. Of course, this part we will take up in the next lesson as well, as we will take up some example there. Well, as we discussed in the last lesson, the algorithm steps for Gauss-Seidel method are: first, what we need to do is find out the bus injections P I and Q I. P I and Q I from the known values of generation, that is P G I, Q G I, and the loads P D I and Q D I at bus I. So, once we know these quantities, we can calculate P I and Q I. P I will be P G I minus P D I, and Q G I minus Q D I will be Q I. So, we first need to calculate the bus injections. After that, we need to form the Y bus matrix for the power network. Then we will set the initial voltages, as we said in the last lesson. Normally we use a flat voltage start, where the magnitude V I is set as 1 per unit and the angle delta I is set as 0 degrees. Therefore, instead of finding inverse in that way, we need to find some other way of solving it, and one of the ways, as we said here, is direct solution of linear algebraic equation using Gauss elimination method. So, here we are trying to see how we can use Gauss elimination to solve this set of equation. Now, what this Gauss elimination tries to do is tries to triangularize this matrix A, which is a n by n matrix, into an upper triangular matrix. That is, all the elements below this diagonal A11, A22, ANN are made 0. So, all the elements here A22, A21 up to AN1, then A23, sorry, A32 up to AN2, and so on, all these will be made 0. If we can do that, then we get an upper triangular matrix as shown here, where all the elements below the diagonal are 0. Now, if we can do this kind of a thing, then finding the solution for this set of equation is very easy, because you can see we know this y n. If we want to find out x n, then we have from the last equation a n n is equal a n n into x n is equal to y n. So, x n is equal to y n by a n n, and once we know this value of x n, then we can substitute this value into this location, because here we have a n minus 1 into n minus 1 into x n minus 1 plus a n minus 1 into n into a x into x n is equal to y n minus 1. So, knowing this value, substituting it here, we have only one unknown x n minus 1, which can be again found out, and so on. We can proceed backward from the nth element, and finally, we can go up to the first element, and therefore, we can find out all the unknowns x 1 to x n. So, this is what we call the back substitution method. So, here, as I said earlier, x n will be given by y n divided by a n n, x n minus 1 will be given by y n minus 1 minus a n minus 1 into n into x n. Now, x n value is already known from here, divided by a n minus 1 into a n minus 1. Similar way, we can write for any general element x k, this will be equal to y k minus summation a k n into x n for n is equal to k plus 1 to n divided by a k k for k is equal to n, n minus 1, so on up to 1. So, x 3 is equal to minus 11.75 divided by 20.5. So, once we know the value of x 3, then from this equation we have 12 x 2 plus 6 x 3. So, 6 x 3 we can substitute the value here is equal to 17. So, that can be brought on this side, then 12 x 2 we have. So, divide this side by 12, you will get the value of x 2. Once we know x 3 and x 2, we can find out the value of x 1, because this equation is 2 x 1 plus 3 x 2 minus x 3 is equal to 5. So, we can, since we know x 2 and x 3, the only unknown here is x 1. So, we can find that from that equation. So, this is how we solve a linear set of equations, and this Gauss elimination method is one which is preferred. There are other methods of solving this linear set of equations, which we call methods of decomposition. That is, we factorize this matrix A into lower and upper triangular matrices, that is LU factorization. Sometimes we use LDU factorizations. There are other methods which are called bifactorization method. All these methods, basic idea is to avoid using inverse and try to find out the solution for A x is equal to y using a direct solution method, that is by trying to factorize the matrix. So, this is, of course, Gauss elimination is the simplest of these methods and is quite effective and is very much used for solving linear set of equations which come out from the Newton-Raphson load flow equations. So, this is what we will do today, and in the next class we will talk how to solve the Newton-Raphson power flow equation using this direct solution method. So, that is all for today, and thank you very much.